Hi everyone, welcome to the lecture for 9.4 on comparisons of series. So we're going to start with Theorem 9.12, the direct comparison test. And it just says that if you have a series where the terms in the series are a sub n and b sub n, then there's a way of comparing term by term that gives you some idea on the convergence of the series themselves. So here we have that every term in a sub n, the sum of a sub n, all those terms are less than the b sub n terms. And so therefore if b sub n, the series, converges, then so does the series of a sub n. So that is, if the larger series converges, then the smaller series must converge. And then also we have that if the smaller series diverges, then the larger series must also diverge. So it gives us a clue on how to kind of approach the convergence of given series. So in example 1, we're looking at the sum of 1 over 2 plus 3 to the n. And for this, we're going to compare it against the series of 1 over 3 to the n. And this is actually the same thing. I can write it, because I have a 1 on top and 1 to the n is always 1, I can write it as 1 over 3 to the n. And this is a known convergent geometric series with r equaling 1/3. And it actually converges to one half. So if you want to review on that, go look up geometric series and then practice computing. There's a little formula for geometric series. So this converges to 1/2. So now what we want to show, so think about this in terms of the theorem up top. We're going to compare it to a known convergent geometric series. So we want to make sure then that the geometric series is the larger of the two, because if the larger of the two converges, then the smaller of the two must also converge. If, on the other hand, the geometric series was smaller than the given series 1 over 2 plus 3 to the n, just because a smaller series converges doesn't mean a larger one's going to converge. So you have to kind of think about what your game plan is. So if you have a known convergent series, you want to make sure that the thing that you're looking at is smaller than it. Okay, so the way that we compare it is we have to look term by term. So we want to show, WTS, want to show that 1 over 2 plus 3 to the n is no larger. Oh, and we need to make sure it's positive as well. We want to make sure that each term in our given series is no larger than the series to which we're comparing, which is 1 over 3 to the n. And the way that we can do this is we can actually flip this upside down and change the direction. So we already know that this is true, the first piece where it's positive, so I don't have to worry about that. And we need to show this. So we want to show this inequality right here. So how do we do that? We say 1 over 2 plus 3 to the n less than or equal to 1 over 3 to the n. We don't know if this is true or not yet, but we're just working with it. And so I can show this is equivalent to 2 plus 3 to the n being larger than 3 to the n. Because when your denominator is large, that makes your fraction small. So this inequality holds. You could also think of it as just cross multiplying as well. But this is certainly true because 3 to the n, right, those are going to be the same value, and adding 2 to it will surely make it larger. So this is true. This is true for all n. So since we've shown that 1 over 2 plus 3 to the n is smaller than 1 over 3 to the n, then the fact that the series of 1 over 3 to the n converges would imply that the series of 1 over 2 plus 3 to the n converges. So therefore, right, so this also converges, and that was because I do want you to notice, though, that just because they both converge, it doesn't mean that they converge to the same value. So we saw a little bit of this before in previous sections from chapter 9, but the geometric series converges to the value 1/2. However, the series that we were given converges to 0.34, whatever. So don't take it to mean that they have the same limit, just that they both converge. Okay, so let's look at another example. So we're going to use the direct comparison test again. Here is our series. So 1 over 2 plus the square root of n. So we know, let's see, how are we going to do this one? Right. So you kind of want to think about known series, like series that you know converge or diverge. And we're going to compare this to the harmonic series. So this is the harmonic series, and we know that the harmonic series diverges. So if we are comparing it to a known divergent series, let's go back up to the theorem again. So if the smaller series diverges, then the larger series must also diverge. So in this case, if I'm comparing to a divergent series, I want to show that it's smaller than the thing that we're trying to figure out, right? So I want to show that 1 over n is smaller than 1 over 2 plus the square root of n. And I don't necessarily need to show this for n starting at 1. It can actually start at any value. It could start at 1,000,000, it could start at 2, it could start at 512. It just needs to be that for some n large enough, all the terms after that point obey this inequality. And that has to do with the fact that the convergence or divergence of a series is not affected by a finite number of terms, right? Because if you're adding or subtracting a finite number, it's not going to change whether or not it converges or diverges. It might change the limit if it does converge, but it's not that the case, you know, infinity minus 1,000,002, that's still infinity. So with that said, we're going to show this, and we're going to observe that there's an n that's a little bit larger than 1 for which this holds. So if I want to show this, I'm going to use the same trick where I'm just going to flip this upside down and change the direction of the inequality. So I get n larger than 2 plus root n. And then I'm going to trick myself into believing that this is a quadratic equation. And the way I do that is I go n minus root n minus 2 greater than or equal to 0. So I move all the terms over to the left, and then I'm going to do kind of like a dummy variable switch. So I'm going to let the square root of n be equal to a dummy variable that I'm calling m. And therefore, n, if the square root of n is m, then n has to be m squared, right? So just squaring both sides. So then what I can do with my inequality is I can express it as m squared minus m minus 2 is greater than or equal to 0. So now I have a quadratic inequality that's easily factorable. So I'm going to get m minus 2 and m plus 1. And I want to know where this is greater than or equal to 0. So if I think about this graphically, I'm going to have a parabola with roots at 2 and negative 1. So here's 2 and negative 1. So that's my parabola. And I know it's opening upwards because the lead coefficient is positive. And beyond that, I don't really care. I'm not super interested in what the vertex is or what the stretch is or anything like that. I just want to know where the roots are and which direction it opens. So I have that now. And I know that, okay, so these are our m values here. So I don't really care when m is negative. I'm just trying to look on the positive side of things. And I can see that the parabola is above the x-axis starting at 2. So I'm just looking here. So this is the place starting at 2. This is the place where my parabola is above ground, if you will. It's above the x-axis. So this tells me that this linear inequality, if I'm considering only positive m values, that so for m greater than or equal to 0, this inequality is true whenever m is greater than or equal to 2, right? So that's really what I'm trying to show you with the graph of the parabola. Okay, so great. So we figured out what m values this is going to hold for. So now we need to translate that back into what n values this is going to hold for. So if I go back to my inequality here, if m is 2, then n has to be 4. Sorry, if m is 2, then n equals 4. So now what I can say is that, therefore, 1 over n is less than or equal to 1 over 2 plus root n for all, which is that upside down capital A, for all n greater than or equal to 4. And so even though we didn't start at 1, we have determined that there is an index for which every term past that point, so that's A4, A5, A6, A7, A8, da-da-da-da, all the way up to the never-ending end of the series, this is always going to be true. And so we've shown that the harmonic series was smaller than the given series. The harmonic series diverges. Therefore, the series that we're given also diverges. Oh, excuse me. Right? So again, just a quick recap. Harmonic series diverges. It's smaller than the one we're given. Therefore, the one we're given also diverges.